Hello? Hello? Are you able to hear me? You've got your computer on mute, so I can't hear you. Hello?
Hi.
Hi.
How's it going?
Good.
Good.
Okay, so it was having trouble starting in, but it seems to be working now. Excellent. So just move back to the beginning. Okay. So I'm going to share screen. So 1 second. Are you able to see my screen?
Yeah.
Yes.
Yes.
All right. So the point of today is to finally get to the point where we can discuss in great detail the project I want you guys to work on together as the research project. So let me just... All right. So what I want to do is I want to just start off with a little bit of a review of some of the stuff we've done and describe some of the types of problems we can do. So I'm going to give you one possible suggestion, which we can then split into several other things. If it doesn't seem like this is exciting you or is aligning with the background you have, just let me know and we'll see what else we can do. But I want to start by reviewing a little bit of the work we did last year, some of the things we were able to prove and some of the methods we used, as well as some of the open problems. All right. Click's not working. Okay, there we go. Okay. So the main goal for this summer is to look at gaps. So last year, we were able to prove results about the number of summons. And when you're doing research, you always start with, what is the first most natural question to look at? And then once you get that and you start going further and further, you start asking more refined questions. So the first thing is just counting how often something happens. Such as, for instance, how many primes are there up to a certain size? So how many, let's just leave it at how many primes are there. And you get the prime number theorem, which is a wonderful result that the number of primes up to x is about x divided by log x. So this means that as you get further and further up, there are more and more primes, but the probability that a number is prime is getting smaller and smaller. So how would you calculate the probability that a number is prime? You look at the number of primes divided by the number of candidates. So if we go up to x, we would have x over log x numbers are prime by the prime number theorem. We divide by x numbers, so we get the probability that your prime is 1 over log x. Then you can start asking more refined questions, such as, what is true about the spacings between prime numbers? And that is significantly harder. So we've known since the 1850s that there's approximately x over log x primes up to x. But it's still unknown today whether or not there's infinitely many primes that differ by 2. So talking about gaps between primes is just at a whole new level of difficulty than just counting how many there are. Now, in the last couple of years, there's been some remarkable advances in understanding gaps between primes. And we have a wonderful result from a few years ago that showed that there are infinitely many primes that differ by at most 70 million. So when you get results like this, you want to think about, what is this number like 70 million? Why would you have a strange number like that? Well, when you're proving things, there's always a tension between two different things. you can try to have the best result possible, which often leads to very technical, very messy work. Or you can have simpler results that are easier to explain, easier to state, but aren't as good. And when you're first proving a result, it's much better to have a slightly weaker result that's easier to explain. And then as time goes on, you see how far you can push it. So we're going to start off by talking a little bit about gaps. So we talked about gaps before, but given that some people were having some questions about gaps, I thought I would just do the gaps again quickly. So the Fibonacci is, we have some indices, I1, I2, I guess R1, R2, all the way up to Rn. And the gaps is just the difference between the indices. So for F1 plus F8 plus F18, the gaps are going to be 7 and 10. You sometimes have to have a decision as to how you want to count things. So could we count the gap all the way up to the very first summon we took? Here the first summon was F1, but what if it was F3? Should I include the gap from the nothingness to F3? You absolutely could do that if you wish, but it's not going to really make much of a difference. So you want to think, what's going to be happening in the limit? So in the limit as n goes to infinity, we have roughly about 0.25 n summons. So if n is huge, the number of summons is huge. So one extra gap at the beginning or the end isn't going to really make much of a difference. And so it's a little bit easier not to have to deal with that, because then we always have gaps just between indices, and we don't have to worry about, well, what happens about that little thing floating in the beginning. So we talked about trying to show that there is a formula for the probability of having a gap of length k. Now, your project is going to be a little bit more involved. Here, we're talking about the probability of a gap of length k. For you, you're going to be talking about initially a pair of integers, and then later on, maybe a triple or quadruple or higher. And so we're looking at some interval fn to fn plus 1. So can somebody remind me, why are we looking at the interval fn to fn plus 1?
Well, because Fn is always included.
Right, exactly, perfect, because then Fn is always included. And so all of our numbers are then roughly on the same setting. So when you're looking at your problem, you will want to have some analog of this to make sure you're studying things that are similar. It's not clear initially that the limit will exist. The hope is that there will be some limit as n goes to infinity, and there'll be some nice function pk. And so, this is the result we proved, a couple of years ago. I don't think we talked about this slide last time. Is that correct? We really didn't talk too much about the first theorem.
I think we talked about it. Yeah.
I think we just talked about the second one, about the Zeckendorf, and we didn't talk too much about the first one.
Mm.
Is that correct? All right, so let's look at the first theorem. So it says for base B decomposition, so base 10 would be a number like 2019, 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 9 times 1. And so for 2019, well, the first thing is we start off with 2 in the thousands place. So that would give us a gap of 0 because we have the same summon twice. Then we have nothing in the hundreds, and then we have 1 in the tens. So we would have a gap of length 2 going from the 2 in the thousands to the 1 in the tens. Then we would have a gap of length 1 going from the 1 in the tens to the 9 ones we have in the ones place. And then we would have 8 gaps of 0. So if you look at the first result, it says for a base B decomposition, the probability of a gap of length 0 is b minus 1, b minus 2 over b squared. And for k greater than 1, the probability is decaying like b to the minus k. So it's very similar to the Fibonacci result. Here we still have a geometric decay. The difference is, we now have a probability of a gap of length 0. does that probability b minus 1, b minus 2 over b squared, does that look like a reasonable answer for you? Is there any test you can do to see if that's a reasonable result?
Wait, sorry. What do you mean by a gap of 0?
So a gap of 0 just means you have multiple copies of the same summand. So that's why I said in 2019, you have 2 places that are giving you gaps of 0. You have 2 in the thousandths place, so that gives you a gap of 0. And then you have 9 in the ones place, so that gives you 8 gaps of 0.
Oh, okay. Makes sense.
So do you think it's reasonable that the probability of a gap of length 0 in a base B expansion is b minus 1, b minus 2 over b squared?
Is there any limitation for B? Like,
So what do you think the limitations on B?
B must be greater than 1, right?
Yes, so if B were to be 1, we can't write anything as just sums of powers of 1. So notice if we try to put B equals 1 in, probability of a gap of length 0 is 0. And the probability of a gap of length k is also 0. And that's essentially telling us that these probabilities make no sense when the base is 1. Good. So the formula is very reasonable in that case. Where else could you test this?
When the base is 2. Like,
Excellent.
Because in base 2, we cannot have 2 summands that are the same. Otherwise, it will just.
Good. So they can't be a gap of. Yeah. So they can't be a gap of length 0 if we're looking at things base 2. And so when we plug in b equals 2 into this formula, we get the probability of a gap of length 0 is 0. And then the other probabilities are all positive. And then the last thing you could do to check and see if this is reasonable is if you take any base greater than 2, then you will get that the probability of a gap of length 0 is positive, and then the other probabilities are positive as well. Well, that makes sense. Once we have base 3 or higher, we can have repeated digits. So one of the things you want to get comfortable with is when you have a complicated formula, can you look at it? Can you find some special cases to build up some intuition? Okay, so we talked about the proof of this result last time. Do people want me to quickly sketch the proof again?
Sure.
Okay, so this is going to be the main thing we're going to generalize, which is why I'm happy to discuss it again. So the first step is we want to know how many gaps there are. And so the squiggly sign means approximately many. So if I have 15 summons, how many gaps do I have?
Um, 49.
Right, so if I have 50 summons, I actually said 50, but that's fine. If I have 50 summons, I would have 49 gaps. If I had 83 summons, how many gaps would I have?
82.
82. So you lose 1 gap, and this is why some people might say, well, maybe you should count a gap all the way up to the first used summon. But in the limit, as n gets very, very large, it's such a negligible amount, it doesn't really matter. So how many gaps do we have? Well, there's fn minus 1 numbers in my interval, and the average number of summons is n over phi squared plus 1. So that is just a result that can be proven with a little bit of algebra. And so I we can calculate how many gaps there are by multiplying the number of numbers by the average number of summons. I technically should subtract 1. I should multiply it by n over phi squared plus 1. I should subtract 1 from that. But in the limit as n goes to infinity, it doesn't really matter if I subtract 1 or not. N is going to be so much larger than that, that's going to become the main term. So are people comfortable with the fact that we don't really have to worry about subtracting 1?
Yes.
So if you want, think of f of n minus 1. If that was, 1,000 to the, let's say it was 10 to the 1,000, then you would have 10 to the 1,000 times n over phi squared plus 1, and then subtract off 10 to the 1,000. Well, if n is tremendously large, the subtracting off the 10 to the 1,000 at the end isn't going to really matter. So the next step is we want to count how many integers in our interval are there such that their decomposition includes fi and fj, but nothing in between. And again, as I said last time, the hardest part in all of these problems is avoiding double counting, is making sure you count things once and only once. So when we get to your project, the difficulty is going to be making sure you only count a given gap once and only once. And what's nice about this is if there's a gap, the gap has two properties. It has a length and it has a start. Once you know the start and the length, then you know where it ends. So if I want to calculate how many gaps are there of length k, well, it has to start somewhere. So that's where the I comes from. And then I just sum over all possible starting values of I. And then I go from I to I plus k. I can stop my sum at n minus k because I have to have a gap of length k. I can't go past the nth summoned. And so the numerator gives me how many gaps are there of length exactly k, and then I divide by the total number of gaps, and I take the limit. And so this was the picture we looked at last time. This is the picture that was causing some issues. So if we can understand this picture, we'll understand completely the proof in the case of the Fibonacci numbers. So I'm trying to use a filled-in circle to represent a number we've chosen, and an X to represent numbers we can't choose. And then anything that's an open circle, we can either take or not take. So this will show the example where we've chosen Fi, we've chosen Fn, and then we can't have anything between Fi and Fi plus k. And because we can't have adjacent things, we can't have Fi minus 1, we can't have Fi plus k plus 1, and we can't have Fn minus 1. So at this point, you need to view what's going on in full. Yes, we have a bunch of summons, and these summons are the Fibonacci numbers, and we can either take them or not take them. But it doesn't really matter what the value of the summoned is. It just matters how many there are, that they're all in a line, and that we can't take two things together. So when we want to figure out how many ways are there to legally choose summons in the first part, or how many ways are there to legally choose summons in the second part, the actual value of the summons doesn't matter. This is just a question in geometry and combinatorics. It's just a counting question. Now, it turns out that the number of solutions is going to be related to the Fibonacci numbers. So let's try to imagine what goes on. So let's look at the far left part. We need to choose numbers from F1 to Fi minus 1. We could choose none of them. We could choose just F1, just F2, just F3, just F4, et cetera, et cetera, et cetera. Or we could choose F1 and F3, F1 and F4, F1 and F5, F1 and F6, and so on and so on and so on. Or we could choose F1 and F3 and F5, or F1 and F3 and F6, and so on and so on and so on. Every legal choice is fine. And we want to know how many legal choices there are. And so the key idea is to notice that this is the same as asking, well, I've got my numbers, F1, F2, all the way up to Fi. How many ways can I choose summons? How many ways can I choose these numbers such that I never choose two numbers that are adjacent and I have to choose the last one? Well, by Zeckendorf's theorem, every integer in Fi plus 1 has a unique decomposition as a sum of non-adjacent items. And how many numbers are in the interval? Well, it's just Fi plus 1 minus Fi. And by the Fibonacci recurrence, Fi plus 1 is Fi plus Fi minus 1. So the number of numbers in the interval is just Fi plus 1 minus Fi, or Fi minus 1. So the number of integers in the interval is the same as the number of legal decompositions. And the number of legal decompositions is precisely what we're trying to calculate. And that's why the number of ways to choose indices from Fi to Fi minus 2 is going to just be Fi minus 1. So this is the key step. I want to make sure everybody understands this step here. So is everybody comfortable with this step?
Yes.
Yes.
Okay, that's one yes,
Yes.
two yeses,
Definitely.
three yeses. Okay. So if I give you F1 to F12 and I tell you I have to take F12, how many ways are there to choose everything?
F11.
F11. What if I give you from F1 to F97 and I tell you you have to choose F97 and everything else is free?
F96.
F96. So now let's look at what's going on in the right. We've chosen Fi plus k. We can't choose Fi plus k plus 1. And now all we need to do is we need to just count how many circles do we have. Because if we throw away Fi plus k and Fi plus k plus 1 and start at Fi plus k plus 2, that one is completely free. We can choose it or not. We have freedom. That's the same as the very far left with F1. And then we go all the way down to Fn, which we have to choose. So all we need to do is we just need to know how many circles there were. So a moment ago, if I told you there were 12 circles and you have to choose the 12th circle, how many legal choices are there? So what would the answer be? If you have 12 circles in a line and you have to choose the last circle, how many ways are there to choose the remainder where you never choose two adjacent circles?
11.
11. Not 11, no.
F11.
F11. F11. So what if there were 97 circles and you had to choose the 97th circle and you can't choose two adjacent? How many ways are there to do that?
F96.
F96. So all we have to do now is we need to figure out how many circles are there at the very end. We can't take Fi plus k and we can't take Fi plus k plus 1, so they're not part of the list. So the first circle that we could take is Fi plus k plus 2. Fi plus k plus 3. We could have Fi plus k plus 4, all the way down to Fn. So the question is just how many circles are there? Well, if I start my circle at 1 and end at 8, how many circles do I have? So I start at F1, I end at F8. How many circles do I have?
8.
I just have 8. I start at F1 and I end at F11. How many circles do I have?
11.
11. So it's really easy when the first circle starts at 1. What if I start at F5 and end at F8? How many circles do I have?
4.
4. What if I start at F5 and end at F12? How many circles do I have?
8.
8. And so the formula is you take the index of the last circle, subtract the index of the first circle, and add 1. Another way to look at it is if I'm going from F5 to F12, let's just shift every index down by 4. So if I shift every index down by 4, I think instead of going from F5 to F12, I'm now going from F1 to F8. I have 8 summons. I have 8 circles. That's all we're doing here, is we're just shifting things down. So because I start at I plus k, at I plus k plus 2, I want to shift that down so that that's now the first summoned. So I have to subtract off I plus k plus 1. And then I would go, and not the last one would not be Fn, but would be Fn minus I minus k minus 1. Okay? So there might be a typo. So we are starting at Fi plus k plus 2. We shift things down by 1, by Fi plus k plus 1. So now Fi plus k plus 2 shifts down to being like the first one.
Mm.
Another way of looking at it is we look at the difference between the two indices and add 1. So it'd be n minus I plus k plus 1 plus 1. So it'd be Fn minus k minus I. And that's where the last formula comes from. So now, question?
I think we need to subtract f like I plus k plus 2 rather than fi plus k plus 1 because fi plus k plus 1 is crossed. Okay.
Right, so the first thing we have is Fi plus k plus 2, but we want that to go down to F1 to be the first thing, not the 0th thing.
Okay.
Right? So since we want it to go down to being the first thing, we subtract I plus k plus 1. Well, another way of looking at it is to just count how many circles there are. It's just the index of the last one, which is n, minus the index of the first thing, which is I plus k plus 1, and then we have to add 1. So you have n minus quantity I plus k plus 1 plus 1. So we get n minus k minus I.
Professor Miller, I think you mentioned last
And
time
so,
that slide is there is a little bit mistake in the slide that the choices.
yeah, I'm looking at this right now, and there could actually be a slight typo that, because then the number is going to be 1 less than that. And so it should be, I think, n minus k minus 1. So I'll let you check that. That would be a really good exercise for you to just go through this carefully and check and see, is there a mistake in the indices by 1? I wouldn't be surprised if I typed it up and missed by 1. It's very easy to make a small mistake like that. So that would be a really good exercise for you to just make sure that you really understand what's going on and how you want to shift things. And so now we just have a product of the two Fibonacci numbers. And so it turns out that there is a formula for the Fibonacci numbers which allows us to handle this and allows us to calculate the sum. So we might talk about that formula later. Right now, I don't know if you're going to need that formula for what you're going to be doing, so I'm not sure how much detail to go into that right now. So this is the general framework of how to handle the gaps for the Fibonacci's. Now we want to shift to the lattice passes. All right. Now, we are not going to be doing too much with Gaussian behavior. So I have the slides here if you want to see the proof. So if you guys want to see the proof that the number of summons is Gaussian, I'm happy to go through and do that now. If you don't want to see that, we can go straight to more stuff on gaps.
So if we are doing our own project, do we need to prove that it's like a Gaussian behavior? If
Well,
not,
that's what we did last summer.
oh,
So last summer we proved things were Gaussian. So it's
we're
a
not.
question of, do you want to see some of the details of what people did last summer? What you are all going to do together is you are all going to work on gaps. And
Oh, so all of us is going to work on the same project, right? The same.
right, and then we're going to break the project into different parts or to have you guys talking with each other, correct?
Okay.
So normally when I have students working with me on a research project, they spend the entire summer, 9 weeks solid, working with me. You're working, 40 to 60 hours a week. We don't have that kind of time commitment based on all the other activities you guys are doing. But we have enough of you that it's effectively the same thing. So all of you together, with the amount of time you have, is essentially the same as what I would have if I had a student just working exclusively on this and doing nothing else. So for most American students, when they do summer research, that's their full-time job. They're working 40 to 60 hours a week. You all are doing many things, which is wonderful, but that's why there's one big project, and then we will split it into sub-projects based on what you guys are interested in. And so I'm going to start off all with the same theme. The thing that's nice about this is you will be able to talk to each other. So when I was in graduate school, it was always nice that my advisor had a lot of people who were doing similar things because it meant that there was somebody you could talk to. I know some of you have already made use of the undergraduate TA and had the ability to just have a couple of sessions saying, hey, I'm trying to understand these arguments. Can you help me out? Now, it's possible that, yes?
So are we going to determine the research, like the, how do you say, the research question, or it's going to be designated by you?
Well, it can go both ways. I'm going to state what I think is a great project for us all to look at. But if there are things that you want to investigate that's related to this, you're absolutely welcome to explore that. And if you would rather explore something different but related, I'm happy to have you do that. The only thing we have to be careful about is how many hours you have at your disposal. So for instance, you have 5 group sessions where we all talk. And then we have essentially, I get 5 sessions with each one of you. Now I've been able to arrange with the program that rather than having just 5 individual meetings, what we can be doing is you can be sending me emails and I can send you comments, and we can have lots of short meetings or lots of just back and forth. You send me a draft, I look at it, and I send you comments. That's far more effective for mathematics than having just 5 long meetings. 5 long meetings is not that useful for us. What's really useful is for you to explore something, get some results, ask some questions, and then run something by me. Hey, Professor Miller, I'm looking at the following. I've seen this. What do you think of this? Do you think this argument is correct? Do you think that this is interesting and worth pursuing? So I'm going to suggest something for us to study as a group. And we can split up and look at different things. And we can just manage amongst ourselves, or you can manage amongst yourselves who's going to be looking at what. But at the same time, if you see something related to this that you want to pursue yourself, you are absolutely welcome to do that. The issue is always just going to be, how much time do you have to devote to this project? You know your schedule's far better than I do. You are doing far more than I ever did. I never got to do research when I was in high school.
Okay.
And I just want to make sure that, for the projects, you have enough time to do it. So last summer, we started investigating some things. And for some of the things, we were able to get proofs. For other things, we were not able to get proofs. In the end, it turned out that we didn't need proofs for everything. We were able to find alternate approaches which said, well, it would have been nice if we'd been able to prove the following, but given that it's resisted analysis, what else can we do? And so I can show you a little bit of the arguments from last summer. And then maybe you will see that something from last summer seems more interesting to you than some of the gaps, and you might want to pursue that a little bit further. I'm just afraid for some of this in terms of how much probability and calculus you need, but it's often not a bad idea to have some motivation for learning material. So let me quickly sketch the Gouchin argument. So I'll first start off by doing the Gouchin for the Fibonacci's, and then we'll talk a little bit about what's needed to do for the simple paths we did last summer. So the first result is that as n goes to infinity, the number of summons converges to a Gaussian. So this is the bell curve or the normal distribution. And the proof basically uses Stirling's formula. So Stirling's formula says that n factorial is approximately n to the n e to the minus n squared of 2 pi n. Now, unfortunately, the proof that I'm going to give you, it might seem bad. It's actually not a bad proof. It's just a lot of algebra. Once you have the key idea to use the cookie problem to count the number of decompositions with exactly case summons, the rest of it is just immediate. It's just Stirling's formula and just doing the algebra correctly. For more general recurrence relations, we sadly don't have the explicit formula for how many summons, how many numbers have exactly case summons. And so the method of proof that I'm giving you here is highly specialized. But it's good because it's the simplest case. It highlights a lot of the key features. So here's the first page of how it begins. So we start off by saying that the number of numbers between fn and fn plus 1 with exactly case summons is n minus 1 minus k choose k divided by fn minus 1. So this is from the cookie problem. Now, if you notice, you see that there's an n minus 1. That's annoying to have an n minus 1. So we're going to just shift everything, and we're going to, instead of looking at fn to fn plus 1, we'll look at fn plus 1 to fn plus 2. And now all the n minus 1s become n's. So now we get fn plus 1 of the probability of having exactly case summons is just n minus k choose n divided by fn. Well, we know what fn is. This is the nth Fibonacci number. We have a really good expression for that, so that's not a problem. Okay, so now, what about n minus k choose k? Well, that's just n minus k factorial divided by n minus 2k factorial, k factorial. And then we use Stirling's formula to substitute for the factorials. And what you'll notice is you'll see that there's a lot of common things. We have an n minus k, an n minus 2k, a k, okay. But I've ignored some pieces. I've ignored the e to the minus n's and some of the square roots because those cancel. So I'm not showing every step of the algebra. I'm showing what remains after we do the cancellations. So all the powers of e drop out. 2 of the square root of 2 pi's cancel. I have the following expression. And now what we want to do is we can write the nth Fibonacci number as essentially 1 over root 5 golden mean to the n plus 1. We have to be a little bit careful. It's always annoying. Are we using the regular Fibonacci numbers where we start at 1, 1, or are we using the ones that give the unique Zeckendorf decomposition? I don't really want to worry about these details and too much. I just want to give you some rough idea. So when we substitute things and we factor things around a little bit, we can write this as the product of 2 things. And this is the line fn plus 1 of k. Now, if you look at it, the first piece involves square roots. The second piece has numbers to high powers. As n gets very, very large, n minus k, n minus 2k, well, k turns out to be the number of summons. That's going to be roughly of size n over 4. So this ratio is going to look like essentially something like maybe 1 over square root of n, up to some constants. It's not going to be getting too large. It's going to look like a 1 over square root of n. And that's essentially because k is some multiple of n. Think of it as about quarter n. So the denominator is going to look something like a quarter of n times n minus half n, and then the numerator is going to look like n minus a quarter of n. So you'll have maybe 3/4 n over a quarter n times a half n. So it's going to look like some number over square root of n. That's going to be the normalization constant for the Gaussian. And that's why that's been pulled out like that. The next part is a little bit more involved. We've got a phi to the minus n, which is nice. And then we've got all these n's and the k's. And so we're calling the two parts the n sub n and the s sub n. And we need to just analyze both of them, and then their product is going to give the probability of length k. All right, so I've remarked that the n sub n isn't too bad. This is actually going through and doing the details a little bit more explicitly. And what we're going to first do is we're going to do a change of variables. So we want to concentrate on the key quantity. What is the key quantity? Well, imagine n is very large. The hope is that most choices of k that have reasonable probability are going to be close to the mean. And that's why we're going to write k as mu, which is the mean, sigma is the standard deviation, and then x is the number of standard deviations we go. So you give me a value of k, and since mu and sigma are fixed, I can write it in the form mu plus sigma x. And to just figure out what sigma is, I just look at k minus mu and I divide by sigma. I should really have n's as a subscripts on the mu's and the sigmas, because the mean grows with n. It's about 0.25 n. But if I did that, the notation is going to get even more involved with just all the subscripts and whatnot, that since n is fixed, I said, let's just let mu and sigma just be simple, and we'll just remember that they depend on n. So if we now want to calculate the first one, the n sub n, we have n minus k, well, we can pull out an n from everything. So we have 1 minus k over n upstairs, and then we have k over n, 1 minus 2k over n downstairs. And what's nice about this is k is growing with n, so k over n is going to be a really nice quantity. And so now we plug in what k is. It's mu plus sigma x divided, it's just mu plus sigma x. So we plug that in, and then just when you finish the algebra, the nice quantities, you define big C to be mu divided by n. And since the mean is n over phi squared plus 1, this is basically just 1 over phi squared plus 1, or by the relations of the Fibonacci numbers, it's 1 over phi plus 2. So this ratio mu of n, it actually converges to approximately a constant. So if n is very, very big, mu of n is approximately big C. And so when the dust settles, we get n sub n is 1 over square root of 2 pi sigma squared. So again, at this point, you shouldn't be following all the details line by line. It's just big picture, what am I doing? I have a lot of algebra. I have a lot of quantities n and k, and I want to figure out what's the right way to look at things. I've got n going to infinity, and as n grows, k grows. Well, k is the number of summons I'm looking at. I could have exactly one summon. And so if I have exactly one summon, then in terms of looking at gaps, I'll have no gaps. Or maybe I have exactly 2 summons and I only have 1 gap. But the point is, it's extremely unlikely to have only 1 or 2 summons. The number of summons on average is about n over phi squared plus 1, or about 0.25 phi. So we have a huge number of summons, we have a huge number of gaps. So it is reasonable to expect that k is going to be decently large. Okay?
Professor Miller, I have a question.
Yes.
If we are doing our project, are we going to do this kind of proof that are very complicated and requires so many steps and algebra?
Well, and again, this is why you are not spending 40 hours a week for 9 weeks working with me. And so I'm trying to give you a sense of why we're doing the projects we're doing. So there's definitely the possibility of doing something like this. Now, a lot of this was done last summer, so there's no need to do it again. I'm going to show you potentially some of the calculations they did, just so you have a sense. And you can see how a big project can be broken up into smaller sub-projects. For problems like this, it's very easy to make an algebra mistake. And so it can take a long time to do the algebra correctly, or to find a good way to do the substitutions. You know, how do I want to write things?
Okay.
So this is just the n sub n piece. Now we have to look at the s sub n piece. And it turns out that the best way to look at the s sub n is to take a product. And the reason is the log of a product is the sum of the logs. And the s sub n piece is just a bunch of products. So if we take the logarithm, it becomes a bunch of sums. So now we have like n minus k log of n minus k. And now we substitute for what k is in terms of mu plus x sigma. And then we pull out the n's. And so the log of n minus mu is the same as the log of n plus the log of, so I'm like, oops. So like over here, I've got the log of n minus mu. I can write this as n times 1 minus mu over n. And that's where, over here, make sure I get this correct. So I'll have the log of n over mu minus 1. Am I writing it correctly? You know, there's so many pieces. We've got the log of, okay, so we've got like a log of mu over here, so this is going to cancel out with pieces over there. So it just becomes a nightmare in terms of what do you want to pull out. So I'm writing this as the log of mu times n minus mu over mu. Things cancel out. I'm going to get a log of mu canceling with something over there. And so it just becomes a tremendous amount of algebra. So now I've got something like this. And now I have, well, I know what n over mu is. N over mu is phi plus 2, so I can substitute that in. And that's why I was pulling out the mu's, because whenever I have an n over mu, in the limit as n gets very, very large, that's going to be approximately something very nice. And so I have all of these different expressions over here, and I get down to this point. And then doing more algebra, what I now have to do is I now have to start expanding the logarithms. So how many of you have taken calculus?
I did.
Okay, so
I did.
let's take calculus.
I have.
Okay, have you seen Taylor series?
Yes.
So the Taylor series of the log of 1 minus x is negative x minus x squared over 2 minus x cubed over 3. So we can expand out the logarithms. And then we can try to see which of the main terms and which terms go to 0. So there's a lot more analysis here. I'm not going to go into that right now because right now the plan is not to do that. This is to just give you a sense of some of the projects. And then just trying to do the analysis and keep track of what are the main terms, what are the lower order terms. And eventually, at the end of this page, we finally reach the point where we're done. So it may look complicated, it may look involved, but once you have the formula for how many times are there exactly case summons, I'm sorry, we're not doing gaps, we're just doing summons. How many times we have exactly case summons, you can just plug that in, use Stirling's formula, and do a lot of algebra. The proof for more general recurrences is sadly more complicated than this because we can't use these techniques. All right. So now let's turn, we've talked about Zeckendorf's theorem before, so I'm not going to go through again. We're going to look at our two-dimensional sequence. And this is now, we're finally getting to the real project I want you to look at. So we'll start off with the first element as 1. And then what we're going to do is we're only going to allow ourselves to move down and to the left. And what we're going to require is that every time we move, we have to move both down and left. You can't move just down, you can't move just left. And once you move, you can then move again if you wish, or you could stop there. So if you want to think of a Fibonacci sequence, and if you want to think of a legal decomposition, we start at Fn, we have a one-dimensional sequence, so we're just moving to the left. And we can never take the same term twice, so we always have to move. And because we can't take two adjacent terms, we always have to move at least 2 steps. Now we have something two-dimensional. We always have to move both left and right on any step. We can never take the same thing twice. And so here is constructing the sequence. So we start over here in the bottom left. We have the number 1. And we're going to fill things in by going along diagonals. So I have to add the number 2 because I want every number to be represented through some path. If I allow myself to move down only, or left only, or down and left only, then I have a lot more freedom. So here, let's allow ourselves to move just down or just left, as well as down and left. If I do that, can I get the number 3?
Yes, 2 and 1.
2 and 1. Can I get the number 4? No, so if I only have the numbers 2 and 1, I can't get the number 4, so I would have to add the number 4. So now I have the numbers 1, 2, 4, and I come over here and I want to decide what should go there. Am I able to get the number 5?
Yeah, 4 and 1.
Yes, how? 4 and 1. Can I get 6?
No.
No. So even though I have 4 and 2, once I choose 4, I can't go down and to the right and get 2, or once I choose 2, I can't go to the left and up to get 4. So I'd have to add 6. Can I get 7?
Yeah, 6 and 1.
Can I get 8?
6 and 2.
Can I get 9?
61.
And can I get 10?
No.
No, because I can't use 6 and 4. So the next number would be 10, then 16, and so on and so on. If I put in the additional constraint that I have to move both down and left, then the numbers would be different. So when we put in the number 4, we put that in because we were able to get a 3 with a 2 and a 1. But if I forced myself to always move both down and left, I wouldn't be able to have the number 3, and I would have to add 3. Now for what you're doing, it doesn't really matter as much. So for last summer, they were trying to calculate how many summons you have in a typical decomposition and show that that converges to a Gaussian. For what you're going to do, it doesn't really matter what the numbers are in the table. You just want to know how many legal paths.
Mm-hmm.
So this is very similar to the calculation we did for the gaps for the Fibonacci's. It didn't matter what the actual values were. It just mattered how many circles there were. I didn't need to know the value of F1 or F2 or F3 or F4 or F8 or F97. I just needed to know I have 97 circles.
Mm.
This is a huge advantage for us, is we don't need to know the value of these numbers. We just need to talk about how many legal paths are there. One quick question. Do you think every number has a unique decomposition, or do you think that there are some numbers that can be written multiple ways?
You mean in the 2-dimensional?
Yeah. Are all decompositions unique, or can you write some things more than one way? So right now you can go down, left, or down and left. I'm not requiring you to go down and left on each term. So can you give me a number that has two different representations?
20. 20 equals to 2 plus 18 and also 16 plus 4.
Good, so 20 has two different decompositions. 24 is 22 plus 2, and that's the same as 18 plus 6. So a lot of numbers have multiple decompositions. So one question you could ask is, how many representations do numbers have on average? And, I think the work we did last summer was close to solving this. Didn't quite solve it. So that might be a project somebody could look at if they were interested, is how many decompositions do you have? Now for that, you would need to know how the numbers are growing in the table. But this is, the type of question you could ask. And a lot of our, goal for these summer talks is to help give you a sense of how do you generate questions. And so as soon as we know that things are sadly different than the Fibonacci case, that we can have multiple decompositions for a number, that we've lost uniqueness, and you can ask, well, how much have we lost uniqueness by? For the Fibonacci's and Zeckendorf, how many ways can you represent any number? How many legal decompositions does any number have?
1.
1.
So the Fibonacci case is very different. In that case, the average number of decompositions is equal to the number of decompositions. Everything is just 1. But here, some numbers have more decompositions than others. So you just showed me that 20, and I showed you 24, both have 2 decompositions. So is it possible that maybe every number from 20 on up has exactly 2 decompositions? So do you think every number has exactly 2 decompositions?
I don't think so.
Okay, so prove it.
Yeah, because if the number is like really small, like for example 3, it can
No.
only be 1 plus 2. Right.
Professor is asking like.
Well, no, I
20
said every number from a certain point onward. Maybe every number from 20 onward has exactly 2 decompositions.
How about 23?
Okay, so how many ways can we get 23? We can do 22 plus 1.
Yeah. I think there is only one
So
way to
that's
do
the only way to do 20.
Yeah.
Okay. So maybe here's the thing. Maybe from some point onward, every number has at least 2 decompositions. So maybe 22 was too small. Maybe 20 was too small. Maybe it's any number that's at least a quadrillion, or any number that's at least a googolplex has at least 2 decompositions.
Mm.
You just proved that. Can you show me that there must be infinitely many numbers that don't have 2 decompositions?
Sorry?
So can you show me that there must be infinitely many numbers that don't have 2 decompositions? What I'm saying is maybe it's just a result of looking at small numbers. If we looked at very large numbers, we might find that every number has at least 2 decompositions. And maybe large is, googolplex, way beyond what we can do, 10 to the 100.
What's googolplex?
Let's just do 10 to the 100. Just do 10 to the 100.
Okay.
So maybe once your number is as large as 10 to the 100, it has at least 2 decompositions. Can you disprove that statement just by looking at this table? So how do you choose new numbers for a table, for the table? What must be true for a number that you've just added?
It has no legal decomposition like before the number. So
Yeah.
like if we prove there are infinitely many numbers in this chart or like diagram, then we can prove that like there's not a number that anything beyond the number has two legal decompositions.
Actually, because any number in the table has precisely one decomposition. Because we can't get it using things before it, and we can't get things using the numbers after it because those are all going to be larger than it. Because we always add the first number that we can't get. So imagine you filled in finitely many entries in the table. How many paths are there? How many legal paths are there? Infinitely many or finitely many?
Finally,
Yeah, if you've only filled in finitely many entries, then you only have finitely many paths. As a quick, really bad estimate, on each turn you have to move at least down or to the left. So if there are 15 elements in the table, you have at most 15 paths you could, 15 steps you could do. So there's only finitely many numbers that you can represent using finitely many elements of the table. So there are infinitely many numbers that aren't represented, so you'll always have a new number to add. So we know that not all numbers are going to have the same number of decompositions. Because, for instance, because we've shown that there's two different ways to get 20, if I take a very large number like 4966, I can add 20 to that, and that will give me two different ways. So, 4986 has two different decompositions.
oh,
It gets worse as you go further and further. So a question you can ask is, how many decompositions do you have on average? What's the distribution of the number of decompositions? That problem, I think, is way beyond anything we can prove in the summer. I think we might be able to prove something about the average number of decompositions, but that will involve some detailed analysis and some real challenging limits, combinatorics, sums, and series. If you wanted to
So,
look at
Professor, can I use a computer
the number of decompositions,
so can I use
yes,
a program to use a computer to prove it, to let it to do the simulation, so which just help us to kind of prove it, to calculate the average number of those decompositions.
So what you suggested is a great way to start, but that is not a proof. A simulation is not a proof, not in a math environment. A simulation is evidence. And the danger is that maybe the behavior changes as you go very high up, and that small numbers could be misleading. So one of my favorite examples is, here's a proof that 40% of all integers are prime. What are the prime numbers between 1 and 10?
2, 3, 5, 7.
So 40% of numbers are prime. How many numbers between 1 and 10 start a twin prime pair, where p and p plus 2 are both prime?
P and what?
So we say that we have a twin prime pair if my number and twice more are both prime. So 3, 5 is a twin prime pair. So what are the twin prime pairs less than 10?
3, 5, and 5, 7.
So 20% of all the integers less than 10 start a twin prime pair, and 40% of all the integers less than 10 are prime. If you go all the way up to 20, how many primes are there between 11 and 20 inclusive?
4.
4. So you're still seeing 40% of all integers are prime. Your primes 11, 13, 17, 19. How many of those numbers start a twin prime pair?
2.
2. You're still seeing 20%. So if we did a simulation like this, we might say, 40% of all integers are prime, and 20% of all integers start a twin prime pair. That's false.
Professor Miller, can you explain
Yes.
again the prime pair?
Yes.
Is it just to pair up the primes?
The twin prime. I'm sorry?
Can you re-explain what's prime pair? Is it just to pair up the prime? Prime pair. You've just mentioned
I'm answering you. The primes are not related to this table. Was that your question?
No.
Or was your question, what is a twin prime?
No, yeah. Like twin prime. What's that?
So a twin prime is a pair of integers that are both prime and they differ by 2. So 3 and 5 is a twin prime pair. 5 and 7 is a twin prime pair.
Okay.
11 and 13 is a twin prime pair. 17 and 19 is a twin prime pair. Now the next prime after 19 is 23. And what's the next prime after 23?
29.
29.
29. And what's the next prime after 29?
31.
31. So 29, 31 would be the next twin prime pair.
Okay. Twin prime.
So we're not going to study, I'm sorry? So we're not going to study primes or twin primes, but I'm just using this as an illustrative example of the dangers we have from doing simulations. If you did simulations on primes and you stopped at 20, you would see that the pattern of 40% of numbers being prime seems to hold. We doubled our range from 10 to 20. You would see that 20% of all numbers seem to start a twin prime pair. So it's not a bad idea to do some simulations. And if you have coding skills, that's wonderful. But it's not going to be a proof at the end of the day. So if you want to try to calculate what's going on with the number of decompositions, that's fine to use computers. I would strongly encourage you to write a program to simulate what's going on. But the calculations are going to get very involved very fast. And unfortunately, it's not going to be a proof. So this is one possibility. It is way beyond what we can do in the summer. You need to use some very advanced techniques, I fear, to look at the distribution of the number of decompositions. It might be possible to analyze the average number of decompositions. That would be an involved project. If somebody wants to try it, you're welcome to it. It is not always the case that the research you try will work. It could be that the problem is too hard, or we don't have the right techniques, or we're asking a slightly wrong question. All right, so let's talk about jump paths. So this is the chance to finally get to what I want us to be looking at for our project. So we're going to look at a compound jump path. So that's going to be a path on our lattice grid. We move only down and to the left. And movements may be greater than 1 unit at a time. So we start off at AB and we want to go down to 0, 0. And so we'll let QAB be the number of paths from AB to 0, 0. So this is good notation. We have 2 subscripts so that we know where we start in the lattice. And we're going to say that any path has to include AB and it has to include 0, 0. And then we want to know how many paths are there with exactly k steps. So we'll call that RABK. So we want to get a formula for this. Now, instead of a compound path, we could do a simple path, where now, for the simple path, you have to have at least one movement to the left and at least one movement down in every step. So rather than using cube, we'll use S for simple. And we'll use TABQ at the very bottom to denote how many simple paths there are from AB to 0, 0. So the summer group last year analyzed what's going on with the simple paths with the T, A, B, K. And then I just had some students at Carnegie Mellon who spent a semester looking at this problem, and they were able to do the harder case, building on that previous work of the compound path. So the compound path turns out to involve more involved combinatorics. All right, so the first are some lemmas about the number of compound paths. And so what I'm going to do is I'm going to just state some things here, and then these are things that you can try to prove. So in terms of homework assignments, just try to get a sense of what's going on. QAB is the number of compound paths, and the claim is it's the sum of the number of compound paths of length k, where k goes from 1 to a plus b. And then for the simple paths, the total number of simple paths is the sum k goes from 1 to the minimum of ab of the number of paths of length k that are simple starting at t, starting at the point ab. So these would be really good things for you to try to prove. If you have any questions, you can contact me and contact the TAs. So the idea is we're essentially partitioning things. We look at all the paths and we split it by how many are of length k. And it turns out that there's a really nice formula for the number of simple jump paths of length k. There is a formula for the compound case, but it's much, much worse. And this is, it's hard to appreciate just what is bad and what is terrible. Remember the long algebra proof we did of Gaussian behavior for the Fibonacci's? Remember how we did that earlier today with the n sub n and the s sub n and the logarithms and all those pages of calculations?
Yeah.
The only reason the proof was that simple is because we had an explicit formula for the number of integers between fn and fn plus 1 or fn plus 1 and fn plus 2 with exactly k summons in their Zeckendorf decomposition. We had that it was a binomial coefficient. And because we had it was a binomial coefficient, there were things we could do. And so we have a similar thing here, where we have a binomial coefficient. And so there's a sketch below as to how you might try to prove this. So as a nice exercise, I would encourage you to try to put in the details and prove that this really is the number of ways to have a path of length k that's simple, starting at AB and ending at 0, 0. So the best way to learn math is to do math. It's hard to do what you're doing is, sitting, listening to an hour-and-a-half lecture, looking at some slides. That's not how you get a real sense of what math is. What you have to do is you've got to put in the hours. You're at a bare minimum, for every minute I lecture, you should probably be spending 2 minutes trying to do math and understand what's been done and prove it for yourself. Now, this is the 2-dimension case. What do you think would happen if we had 3 dimensions? We have T, A, B, K is A minus 1, choose K minus 1, B minus 1, choose K minus 1. What do you think would happen if we had 3 dimensions and we had a point A, B, C as the start?
And also C minus 1, choose K minus 1, right? Just multiply.
Yeah, and in fact, yeah, excellent. And in fact, if you look at the one-dimensional problem, the one-dimensional problem now just becomes, I start at the point A, I've got to go down to 0, and I have to move it each time, and I can choose adjacent things. And if you think about it, that's going to give you the A minus 1, choose K minus 1. All right. So it is possible to do, Gaussianity proof. I'm just quickly going through this so that you can always just hit pause on the screen. And this gives you, some sense of what we were doing last time. And we were able to deal with it. And so now it's time to finally talk about what I want us to do for the summer, for the very first thing. So I'm going to go back to the gaps, and we have the sequence over here. So what I want to do is I want to look at, say we choose 1522, then 296, then 94, then 16, then 1. I want to look at the gaps that I have created from this. Okay? And I want to know how often do I have various types of gaps. So over here, this is the point 1, 1, 2, 1, 3, 1, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5. So this is the point 4, 5. So I go from 4, 5 to 4, 4. What is the gap between those?
Is that 1?
It's not 1. So try again. You're close, but it's not 1.
It's 8.
It's not 8. So we're going from 4, 5 to 4, 4.
Is that 0, 1?
It's 0, 1. So the gap is now going to be a pair.
Okay.
When you're talking about gap, are you asking like the gap in the like in the coordinate, or you're asking the gap in the terms? Because if you're asking the gap in the terms, then I think it's 8. Yeah.
So why would it be 8?
I mean, because if we just label each number with their according like fi, then the difference between these terms is 8. I mean, like for example, if 1 is f1, then 2
Yep.
is f, then I think the gap is 1, right? Because like how to say? Maybe I can give another example. Like
No, I understand what you're saying. So you're saying this is the first element, second, third,
yeah.
fourth, fifth, sixth, 10th, 11th, 12th, 13th, 14th, 15th,
Yeah.
16th, 17th, 18th, 19th, 20th, 22, 23, 24, 25. It's 1, 2, 3, 4, 5, 6, 7, 8. And so it'd be 8 later. You can absolutely use that as your notion of what the gap is. And that might be a better thing to look at. So this is where it's nice that we have so many people. So absolutely give each one of these numbers an index. But if you do that, you've now made this a one-dimensional problem, right?
Oh.
So you do have it so that this is now a difference of 8. You've got all of these numbers now lying on a line, and then you have a strange rule as to which number can you use next. It's not immediately clear now if you have a number, what number you could use next.
Okay.
Right?
So we're still using like 0, 1, right? To show the gap. Not the difference.
I mean, I'm with this is 1, 1, and then we imagine that there's a 0, 0 here that we just have to move to. So it's not wrong to say that they differ by 8. But if you do something like that, we've now put all of our numbers onto a line, and it's not immediately clear. If I give you the 38th point in the sequence, what point can I go to next? It's not clear. I would have to figure out where does that point lie in the lattice to see which points are now accessible from it.
Okay, I think I understand. Yeah.
And that's why it's not a bad thing to look at. I just don't think it's going to be the right thing to look at. So what I would say is the better way to look at it, the way that I think might be more tractable, is if you have an index 4, 5, and you go to the index 4, 4, that's a gap of 0, 1. And then if we went from 4, 4 to what did I say we went to next? Let's make it 112. Then we go to 2, 4. Then that would be a gap of length 2, 0. And if we came down to here, we'd be going from 2, 4 to 1, 2. So that would be a gap of 1, comma 2. So is it clear what the gaps would be in this case?
Yes.
So now we're ready for the project that I want us to all be looking at. And we still have another lecture or two. But the problem I want you to look at is, what can you say about the distribution of gaps? Does it converge? Does it converge to something nice?
I think I have a question. Like, I think
Yes.
this gap is quite different from the gap that we encountered before, because previously the gap are just numbers, but in this case it's
Correct.
the difference between the coordinates. So how are we going to use numbers to represent this gap, and how do we show that in the distribution?
Well, I'm not going to say anything, and I want you to think about that for a week. I have an idea. I have 2 different ideas of how to look at it. But I want to give you guys some time to think about how would you define the gap now. Because I agree that 2, comma 4 as a gap seems very unsatisfying. It's not a nice number like we had before. So I will leave that as an exercise for you to think about as to how do we want to define what the gap should be.
Okay.
Because it's not clear now. I don't think using the index is the right way, just because I think that's going to lead to something that's just too painful to analyze. But if we use the pairs, we're not going to get a number. So I have 2 ideas on around this. I'm not going to say that. I'm going to leave that for you guys to think about.
Okay.
But we finally reached where you now have research problems to think about. And a lot of times in math, the hardest thing is figuring out what to study. All right, so this is a good place to stop. I'm going to work on getting the video uploaded. Have a great evening. Well, I guess a great day from where it is for you. It's about 2 a.m. where I am here.
Cool. Okay. Good night.
Good night. Good night. Let's see if I can.
Professor,